Alright, what's up? In this video I'm going to show you how to use the first derivative to find extreme values. So let's take a look at this one example and we're going to really break it down. So we're going to find for this function right here below. So for the function below, which is 1/2 x minus sine x, and we're going to give it a closed interval, 0 to 2 pi. We want to find any extreme values. Remember, extreme values are max or minimums. Okay? Now, what we're going to do is we're going to use the first derivative to do this. Okay? And I'm going to draw it out and kind of let you know about the theory as I kind of work step by step. So, based on what I'm looking at, right, here's the particular function, and here's 0, and here's 2 pi. And I'm looking for the highest and lowest point, right, and any potential local max or mins along the way. So it appears as if this point right here is my local min, right? And it appears as if this point right here is my max. Excuse me, that being the min and that being the max. Okay? So what I want to do is I want to use the calculus to find those x and then the corresponding y values and justify y, be a little bit more rigorous about this. Okay, so some things to remember. First and foremost, if this function is continuous on this closed interval, right, which it is, right, this function right here is continuous on this closed interval, 0 to 2 pi, then the extreme value theorem assures us that there must be a max and min somewhere. Okay, so we got that going for us, which is good. So we also know a couple things about the first derivative, which we just began to start to develop. First is that we have a potential maximum at critical points, okay, that being when the first derivative equals 0. We focus on those points because those are the points at which the function could potentially be changing from increasing to decreasing. All right? And remember, when a function is increasing, its derivative is positive. When a function is decreasing, its derivative is negative. Okay, so that's why we use the derivative for this analysis. So here we go. I'm going to first take the first derivative, and the derivative is going to be the derivative of 1/2 x, which is 1/2, minus the derivative of sine of x, which is cosine x. Okay, so that's my first derivative. What I want to do is find the critical points. Okay, so my critical points are when the first derivative equals 0, and that is what I structure my analysis about. Okay, so actually I should add to that, does not exist for the first derivative. But this first derivative is fine everywhere, so this is not even relevant for this particular problem. We'll get into problems where it is relevant. So in any event, I want to find where the first derivative equals 0. I want to find horizontal tangents, right? Because right here I got a horizontal tangent, 0 slope. Right there I got a horizontal tangent, 0 slope. So I want to find where that happens. Right? So that's going to happen when the derivative, 1/2 minus cosine x equals 0. Of course, that means the cosine will be 1/2, right? And so when is the cosine of x equal 1/2? Well, again, we're thinking about on the interval 0 to 2 pi, right? Okay, so the derivative will equal 0 when the cosine of x equals 1/2. So let's kind of think about what that means back from the unit circle. Cosine, remember, is the x value, right? So I want the x value to be 1/2 of my triangle, my reference triangle, right? So here's my x value of 1/2, right, in the first and fourth quadrants. Okay, that 1/2 you might remember is across from, if the hypotenuse is 1, it's across from the 30-degree angle. So that means this angle right here is 30, which would mean the reference angle right there is 60. And in radian language, that's pi over 3. All right, so one solution is pi over 3. Okay, but there's another solution all the way over here in the fourth quadrant. Again, with the same reference angle of pi over 3 radians. Right? But we have to travel. So basically we travel the whole 2 pi minus this reference angle of pi over 3. And 2 pi, which is 6 pi over 3, minus pi over 3 is 5 pi over 3. Okay, so those are my two critical points, right? Points at which my derivative equals 0. And on the graph of the function, right, that's this point right here. So this x value right here is pi over 3, and this x value right here is 5 pi over 3. Okay, I'll find the y value in a little bit. Okay, so I found my critical points. those are potential maximum values. They don't have to be. In this case, they are, but they don't have to be. And so I want to just make sure that those really are critical points. Okay. So what I'm going to do is I'm going to set up a chart. And I'm going to set that up down here. So this is just to make sure. So let's be sure. Right, so my derivative again is 1/2 minus cosine of x. And what I'm going to do is I'm going to set up a little chart which kind of brings a lot of these ideas together that we're going to use, right? And the chart is built about the critical points, which we found are going to be pi over 3 for x and 5 pi over 3 for x, right? And those are the points at which we have horizontal tangent, zero derivative. All right, that's what we just found here. Okay. What I want to do is kind of look around those points, right? So, oops, sorry, that should be the function, right? Remember, we're analyzing the function y, right? We're just using the first derivative to analyze it, right? That's our goal. So at the very least, the function y has horizontal tangents at these two x values, pi over 3, pi over 3. Okay, and let's see why they are, in fact, max or min values. What I'm going to do is I'm going to graph quickly the derivative, right? And so, actually I can just sketch it really. So here's what the derivative will look like, right? So cosine x is here, right? So minus cosine x will be the opposite way, right? It will look like that. Okay? So if I add a half to that, it's going to bump it up 1/2, right? So here's essentially what our derivative is going to look like, right there, right? That's a rough sketch of our derivative, okay? It's using a little graph translation theorem. So what we found really are these two zeros of the derivative, pi over 3, and right over here, 5 pi over 3, okay? And so what I want to evaluate is the sign of the derivative around those critical points of pi over 3 and 5 pi over 3, right? So if I look to the left of pi over 3, here's an x interval, right? And if I look to the left of pi over 3, right here, my derivative is negative, right? How do I know negative? Because it's below the x-axis. Those are negative values. So to the left of pi over 3, my derivative is negative. Now what that means is on that same interval, therefore, the function will be decreasing. Okay? Remember, whenever the derivative is negative, the function will be decreasing. Negative slope, going down function. Okay? From pi over 3 to 5 pi over 3, again, these are x values, okay, on this interval, my derivative is positive, right? How do I know it's positive? Because it's wholly above the x-axis, right? It's positive. These are all positive y values on this whole green stretch of the derivative. So that means from pi over 3 to 5 pi over 3, my function is increasing. Why? Because that's where the derivative is positive, right? This green stretch. Okay? Finally, after 5 pi over 3 to 2 pi, we're back down for the derivative in negative land, right? How do I know that? That's correct. It's below the x-axis. So after 5 pi over 3, remember we're stopping at 2 pi, my derivative is negative, which means after 5 pi over 3, my function to 2 pi, my function is decreasing. Okay? So here's a correlation here, right? Negative derivative, decreasing function. All right? Positive derivative, increasing function. All right? So the derivative tells me a lot about where functions are increasing and decreasing and where we have changes of behavior. Changes specifically in this case from decreasing to increasing, and then again from increasing to decreasing. Okay? So here's what I know now. Okay? Based on pi over 3 being the point at which the function y changes from decreasing to increasing, that makes pi over 3 a minimum, right? It goes down, stops, then goes back up. So let's take a look at the original function, which we've lost sight of. So here's pi over 3, right? Up until pi over 3, we're going down, stops, and then we go back up. And we go back up all the way until 5 pi over 3, right? And at 5 pi over 3, based on this analysis, the function changes from increasing increasing. Right? We're increasing up until 5 pi over 3, positive derivative. And then we change to decreasing at 5 pi over 3. Which means that if a function increases and then changes to decreasing, the point at which it changes, in this case 5 pi over 3, is going to be a max. Okay? So this chart here just justifies what's happening visually in the graph of this function. Right? Specifically that this point right here, right, whose x value is pi over 3, has to be a minimum. Right? And of course we knew that because it just looks like it is a minimum. Right? But the calculus behind it justifies that pi over 3 is the x value where this function changes from decreasing to increasing, therefore making that point a minimum. Okay? This point right here, 5 pi over 3, is the point at which the function changes from increasing to decreasing. And we use the derivative and the sign, particularly the derivative, to find that. Therefore, that has to be the max. Okay? So min at pi over 3, max 5 pi over 3. So how do we get the min and max values? Remember, those are y values, right? Well, the way we get those is just by plugging them into the function, right? So I'm going to plug in pi over 3 and 5 pi over 3 to the original function. So I know, here's what we know so far. We have a minimum at x equals pi over 3, right? So how do we get the y value? Well, I'm just going to take the function I'm analyzing, plug in a pi over 3. So it's going to be 1/2 of pi over 3. What was the original one? Minus sine of pi over 3. Right? So 1/2 pi over 3, of course, is pi over 6. Minus, and then the sine of pi over 3. What's a sine of pi over 3? Let's go back to the unit circle, right? And rotate pi over 3. Remember, that's 60 degrees. And it's a side opposite that. So here's my pi over 3 degree angle. Pi over 3 is 60 degrees. And so the side opposite is root 3 over 2. And remember, that's my y value, the sine value. Okay, so this, actually I can clean it up a little. Let's use a common denominator of 3. And we'll call that pi over 6 minus 3 root 3 over 6. Or pi minus 3 root 3 all over 6. Okay. So what that means is this actually is the minimum value, right? It happens here when x is pi over 3. Okay, but the minimum value that this function attains over the closed interval 0 to 2 pi is, let's go back, I forgot what it is. That y value, pi minus 3 root 3 over 6. Okay? This here is the minimum value. Right? Of course, it's the y value. The maximum value, I'm going to plug in 5 pi over 3, right? Because I know that's where a max happens. So I'm going to plug a 5 pi over 3 in for x. So max when x is 5 pi over 3. So f of pi over 3, 5 pi rather, over 3 is equal to half of that x minus the sine of that x. Again, that's the original function. 1/2 x minus sine x. Right? So that ends up being, oh my gosh, 1/2 5 pi over 3, that's going to be 5 pi over 6, minus the sine of 5 pi over 3. Pi over 3 is 60, right? So 5 of those pi's over 3 is going to be almost all the way around, right? 6 of those pi over 3 would be the whole circle. So I'm going to go every but pi over 3. There's my reference triangle. Reference angle, of course, is pi over 3. Right, and the sine is the y value. It's this piece right here. Right? Pi over 3 is 60. Across from 60, if the hypotenuse is 1, is root 3 over 2. In this case, it's negative root 3 over 2, because I'm down in the fourth quadrant. So the sine of 5 pi over 3, therefore, is negative root 3 over 2. So we end up subtracting that, which adds that root 3 over 2. Okay, and again, now to have a common denominator, I get 5 pi plus 3 root 3 all over 6. Okay, so that is the maximum value. It happens here, right? But the actual maximum value is the y value, 5 pi plus 3 root 3 all over 6. So therefore the max is 5 pi plus 3 root 3 all over 6. Okay? So that's kind of a complicated way to justify something that's pretty obvious. Okay? But nonetheless, it is how we can use the calculus to find max and minimum values. Okay? So we find the critical points to summarize, right? Here are my critical points where the derivative equals 0. We found that those are pi over 3, 5 pi over 3. Right? Boom and boom. Right, and then we just make sure that those are, in fact, max and min. So just because we have critical point where the derivative equals 0 does not necessarily mean those are max or min values. Right? We're looking for a sign change in the derivative, negative to positive or positive to negative. Right? And negative derivative means decreasing function. Positive derivative, increasing function. Right? And then once we are sure, we kind of plug those x values back into the function to get the min and the max, because those are y values, the min and maxes. Okay. Thanks for listening. It's a fairly complicated problem. We'll go over some more basic ones tomorrow, and then probably a little more challenging one tomorrow too. So come in with questions. Bye-bye.